So let us start today's lecture, and let me start with a quick review of what we were discussing last time. So these were some of the main concepts. You have a population, and you have elements in the population. There's some value you can assign to those elements of the population. There's some characteristic. Each characteristic is given some value, and for each member you have a certain value. So if you count that value for all the members of the population, you add them all up and divide by the total number of population. That's just the arithmetic mean, and that's written over here. So you take the values for each member, add them all up, and divide by the total number. So there's a sum over all elements in population. But the same thing you can also compute using this formula, where now you are not summing over all elements in the population, but rather all possible values in the population, all possible values of the variable in the population, and you are dividing, and you then multiply them with the probability of the uh, corresponding value, and then you compute the sum. So for example, in our example where we had these numbers, so one way to compute this would be just add all these up and divide by the total number. So that's like I'm taking each element and adding them all up. But you can do the other method where you list all possible values. There are only 5 values which are possible in this population, and each one of them comes with a certain probability. For a finite population, the both formulas are same. You can derive one from the other. But when you're talking about an infinite population, then only this thing makes sense. Because you have infinite number of elements, you can't add them all up. You just line up all the possible values, and you are given some distribution, some probability distribution. So you use this formula to compute the mean. So that's the population mean. Now what you can do, you can pick a sample from this population, and now this time you compute the mean for the values which you have got, or elements you have got in the sample only. So it's exactly the same concept, but if you do it inside a sample taken from the population, then it would be called the sample mean, and is denoted by x bar. Unlike the mu here, mu would stand for when you are computing this mean for the population, and when you're doing it on the sample, it's just x bar. So again, all elements in sample, sum them up and divide by the total elements in the sample. So like if you are sampling with 4 elements, they all 4 can have same value. That's okay. You add all of these and divide by this sample. And but you can compute this. This is the sample mean, and the sample mean is a random variable. Every time you draw a sample, you get a different sample mean. So the goal is to see what is the probability distribution of the sample mean. Sample mean is a random variable, and we want to see its probability distribution. So because every time we are getting a different answer, we want to have an idea that how this random variable, how it's behaving. What can we say about this probability distribution? So the first thing you can talk about to quantify this probability distribution is the mean of the sample mean. Since sample mean is a random variable, So you compute its mean. So you can call it expectation value just to make it a little different from the mean appearing here. And this, you use this formula because in principle, how you are doing it is that you are picking up samples and computing the means, and you repeat this process an infinite number of times to get the true mean, to get the true expectation value. When you do that, when you are, so you have these possible values of means. So suppose these are the possible values of means. You draw their probabilities, whatever the probabilities are. So over here you have values, and over here you have probabilities. So when uh, so using these to compute these probabilities, in principle, you will have to take infinite number of samples. Or what you can do is that if you can derive this probability distribution by counting all possible samples, if you have a finite population, you can count what kind of, how many samples, what different samples you can pick. And from those samples, you can derive this probability distribution. But suppose even if you don't know, we just want to quantify that what can we say about this probability distribution. So the first thing you can do is you can talk about its expectation value or the mean of this probability distribution. This is a distribution and you want to find what is the central value of this distribution. So let's explain it with our example. So from this data, 2, 4, 6, 6, 7, 8, we pick samples of size 2, and I have listed all possible samples, samples without replacement. And you can't do anything else. In this first box, in this box, all possible samples are there and their corresponding means. So I can list what mean values are possible if I do the samples of size 2, and these are the possible means. And total possible samples, because each sample is equally likely, and the total samples are 15, so I can just give the means a probability distribution, because 4 appears 2 times in possible samples, so its probability is 2 by 15. 5 appears 3 times, like over here, so its probability is 3 over 15. And here you can draw this probability distribution. 3.5 does not appear, so it has 0 probability, and all the other means their probabilities are listed in this. This kind of graph is called a histogram, where you are listing all possible values or maybe a range of values, and for each value you are either showing the frequency, that how many times it appears, or the probabilities. Yeah, I'll take a pass. So now from this sample, from this data where I have listed all the samples and their probabilities, I can use this formula to compute the mean of the sample mean, or expectation value of the sample mean. So you just take the value, multiply by its probability, add to the next value, multiplied by its probability, and so on, and you get this number 5.5, which actually happens to be also equal to the population mean. Somehow it's just a coincidence at this point that I took samples. Each time a sample gives me a different mean, but since I know what are their probabilities, in this case, I know what is the probability distribution of the means for samples of size 2, I can compute what would be their expectation value of the sample means, and it turns out that it would be 5.5 as well. And so you can compute it this way or compute it this way. Sum of means of all possible samples divided by all possible samples. So what I could have done, just start adding these means over here and over here and divide by 15, total number of samples which are possible. It will give me the same answer. And it turns out that the answer is equal to the population mean as well. So is there a question?
Yes, sir.
G.
Yes, sir.
So one by
That's
one.
my go on.
It's okay, Shahrukh, you can go first.
Sir, my question was कि जो आपने म्यू लिखा है, won't
Hmm.
that be x bar? या फिर आपने
No,
या फिर म्यू
mu
होगा?
in principle is different. Mu is not x bar. Mu is when you compute the mean of the population, and x bar is when you are taking samples and you compute the mean of the sample, of one sample. So that sample, took a random sample, you just added its value and you got a number. It won't be equal to this. So x bar is not equal to mu. Like over here
Uh,
in this data, these are x bars and they're not equal to mu. Mu is 5.5. Only one of them is equal to mu.
okay,
However,
thank you.
when I compute the expectation value of the sample mean or mean of the sample mean, that turns out to be equal to the population mean. Yeah,
Okay,
so
sir,
there was
thank you.
another question.
Yes, sir. I just want to confirm that in this example, you've taken the population of 6 elements, and then you further narrow them down to a sample of 2, if I'm not mistaken,
Yeah,
right?
yeah.
All right. And I just want to confirm another thing. When it comes to expectation value, you're taking an average. So is this like the most central value that the average would come out to be? And like, how would it be represented?
Yeah. So you can see, yeah. So what this expectation value of the sample means is samples means they have become a random number. So they take different values and they are plotted over here. So they are distributed. It's not one value. So this, and you want to quantify this distribution. What can you say about it? So one thing you can say about it is that what's the kind of central value over here? What's the mean? What's the average? So one measure of centrality, central value of a distribution, it's up to you how you define it. So one measure is the mean, that you just add all of them and divide by the total number, divide by and taking into account how likely one value is.
Got it. Thank you.
Mhm. So let's do the same example but change the sample size, and this time we are taking samples of size 5. So over here are listed all possible samples of size 5 without replacement, and you get, and then you just compute their sample means. So how did I get this 5? I just add these numbers 2 plus 4 plus 6 plus 6 plus 7 and divide by 5. So you got this 5, 5.2, 5.4, so on. And I can draw this kind of histogram and to place them equally at equal spacing on this scale, you are going at steps of zero point 0.2, and which exhausts all the possible values which are there now uh, in your data, which has the all the sample means, and you have also drawn their probabilities. So one thing you can notice, it will be interesting later on, that when I had the samples of size 2, then the mean was hopping between 3 and 7.5. The mean of the sample mean was hopping between 3 and 7.5. But this time that range has narrowed down. It's hopping between 5 and 6.2. But we can still calculate its expectation value. And again, using that formula, I get This is not a sample of size 4, this is sample of size 5. You get same number 5.5, which is equal to the population mean. Actually, you can try it out. No matter what sample size you take, the sample mean, the expectation value of the sample mean is always equal to the population mean. So this
Sir,
is, yeah.
as we're getting the same mean for samples and the whole population, can we say that this we're getting the same value because we're using the whole of the population in the samples?
No, we are not. That's not the reason. It's just a mathematical fact. You are not taking the whole population as a sample. You take a sample of any size.
No,
Computers.
we're like taking all the values in the population as samples, as different samples, but we're still analyzing every
Yeah. You
value
can
in
say
the
that. You can say that.
population. And that's the
Sir,
reason we're getting the same value.
Yeah, you can say that.
sir, can you please explain the formula for both of these, the sample mean and the population mean?
Well, let's stop here. Let's not look at this for now. Let's remove it. The population mean is just you add all the values, all the elements in the population, and divide by the total number in population. That's just the mean. But you can do the same thing if you know the frequency, if some certain values are repeated, because you have to add all the elements. Some elements, like over here, let's give them names: A, B, C, D, E, F. So like element C and D have same value of 6. C and D have same value of 6. So this sum you can do in terms of frequencies, right? So for example, I can do 2 plus 4 plus 6 times 2. This is the frequency of 6. Because I have to just add. So instead of adding, I can just multiply by its frequency. It will still give me the addition. Plus 7 plus 8 and divided by 6. But when I do this, I can collect this. So I can write it like this. And what is this giving me? This is giving me frequency of a particular value, how many times it appears, that value, divided by the total number, which is just the formula when this n is large. This is the formula when you try it again and again. This is the formula for the probability. So that's the idea of this formula, that you can do this, or you can do it in terms of frequencies, or if you are considering an infinite population, you can just take the probability distribution and do this. You do exactly the same thing, but this time you have just picked up a sample and you
Alright,
just
sir,
do
thank
the
you.
arithmetic mean formula. You will get a value that would be called the sample mean. So you should think of it this way. You have a population, a really large population, and suppose you don't know its mean. You want to know its mean, but you don't want to add all the numbers. You don't have access to it. So you pick a small sample. Let's say you pick 10 numbers and you are hoping that since I've picked up randomly, then when I'll compute the mean out of these 10 values, I will get something close to what the mean of the population is. So that would be the sample mean. So this is what you call a statistic. Some value which you have computed using a sample. And when you try it once, you also call it a point estimation. This is also the term which people use. So you wanted to compute something, but instead of doing it on the whole population, you took a sample and estimated it. And you are just hoping that will it be that it would be close to what the true answer is. Well, as we see in this example, the true answer is here. We don't get it. Every time you will pick a sample, you will get a different answer. So you know that you won't always land here. So you want to quantify where would you land? What can you expect? That what will be the value in a random sample? So that is the kind of question we are trying to answer. So how would you answer? You would be able to answer if you knew this probability distribution exactly. In this case, we know because we have constructed everything by hand, but we are trying to answer that when we don't know this probability distribution, what can we say about this probability distribution? Well, the first thing we have found out that we can say that this distribution, its central value, its own mean. So that's the mean of these means. That is same as the population mean. And it's an extremely important result. Proof is not that important because you won't be tested on any proofs. But this result is extremely important. That the expectation value of the sample mean is equal to the population mean. It's a random variable, sample mean is a random variable, but it's distributed around the true population mean. So at this much you are guaranteed that it will hop, but hop around the central value which is same as the population mean. So I hope this answers the question. There's some other question. Well, how did I obtain the population probability values for a sample of size 5? Very simple. I just listed all of these, and what I find is that this sample, this one of 5.4, this I can get in two ways. Because in the population, I had uh, two sixes. So when I pick, there's a possibility that I'll pick this guy, this guy, this guy, this guy, and this guy. So that will create this sample. But randomly, instead of this guy, I can pick this guy. It will give me the same sample and same mean, same kind of looking sample, but with a different element. So it will appear twice. It can appear from two different random samplings. So both of these, like picking this guy and picking this guy, have equal probability. So the combined probability of picking 1, 6 and the rest 2, 4, 7, and 8 becomes double compared to the other lots. So that's why you get a 2/6, which gives you 1/3.
Sir, I got that. Thank you so much. But when it comes to like having the two sixes in the sample, what about then? Because they're the same element when you think about it. Wouldn't that also be double counting in a way?
This guy?
Like for example, can we imagine it to be like there's like 6-1 and 6-2? Like, as in there are two types of sixes. Let's just say that. So in the other samples I've created, the other 5, actually there are 5. Sorry, in the ones that you have two sixes, wouldn't it matter? Like the order matter? Like
No,
we
order
shouldn't
doesn't
square it.
matter.
All right.
Order won't matter. You're just picking because you're not replacing, so order doesn't matter.
Got it. Thank you.
So you can just look at the proof really quickly. So what you have over here, you have a random variable, which is x bar, and this is composed of, you pick one, you pick the second, you pick the third. You're picking a sample of size n. Each one of them, and I'm assuming that the population is very large. So it's kind of very large. So each one of them is a random variable. And we saw it last time, like when I'm picking one random variable from the population, the probability of getting this is actually the same as the probability distribution which you have constructed for the population. So when you compute, you are taking these n variables and dividing it by the total number n. And now you want to compute the expectation value of this guy. So how would you compute this? By the formula. Now I don't know how much you remember from your last course, so I'm just gonna quickly go over this proof. If you don't get it, don't bother. I pick this 1, 2, 3, these random numbers. So now I'm picking some value for this guy, first guy, which I call x1, x2, x3, xn, and I multiply it by, as my formula says, multiply it with the probability of getting x1 for the first variable, x2 for the second, x3 for the third, and so on. So you remember from the rules of probability, if you have and in the probability statement, that x1 for the 1 and x2 for the 2. So that would mean that you multiply those probabilities. And where are these probabilities coming from? These are the probabilities in, this is the probability distribution of a single variable, of a single random element picked up from the population. So it's the probability distribution of the population. So now you can just take it in. You are summing over all these values, all possible values, on summing over x1, x2, x3. They can take all different sample values. So you get this kind of a thing. x1, px1, px2, px3, pxn, plus x2, px1, px2, pxn, and so on, divided by n. And you're summing over x1, x2, x3, because all samples are possible. When you sum over all these, this gives you the mean in the population, because this is the formula for, this is the random variable from the population, this is the probability distribution of the population, so it computes the mean according to the formula. When you sum over this, this is not being multiplied by anything. When you sum over all probabilities on the second variable, gives you 1. Gives you 1. All of them gives you 1. Similarly, over here, px1 when summed gives you 1. x2 times px2 summed gives you the mean value of x2. But x2 is same. Is the same variable which you have picked from the population. Is just you are just writing a different name for it. You're just picking one guy from the population. So that's also mu. You get n mu's divided by n. So you get mu. So this is like a short proof that expectation value of the population mean is equal, of the sample mean is equal to the population mean. Doesn't matter what is the size. This n doesn't matter. Any size you pick up, you always get the same expectation value, which is equal to the population mean. So what it's actually saying is that whenever you pick samples and then you draw the distribution of sample means, then this distribution may look weird, but it will be centered around population mean. Samples mean will be spread around the population mean. So that's the main lesson over here. Now you want to quantify even further, what else you can say? So this kind of theorem you have proved is true for anything. Any example you take, any number of samples, any size of sample you take, this is always true. So this is good to know. But you also want to say something about how much is the spread in this distribution of sample means. So to quantify that spread, you can use this thing which you have cooked up, which is called the variance of something. And in this case, we are looking for variance of the sample mean. So you can recall that whenever you have some data spread around, some mean value, you can quantify the spread by defining the variance. So what is the variance? So you have some data points, and so suppose let me draw a scatter plot. You have some index. Index means you are counting all the data points, and these are the values. 1, 2, 3, 4, 5, 6. So first is 1, second is 2, third is again 1, fourth is 1, fifth is 4. This one over here, like this. So you can have more than one value, same value for more than one element over there, and they are all spread around different value, but they will have a mean, which I have written over here. And you want to know that how much is the kind of average spread around it. So the best thing to do is that you compute the average of the spread. So what is the spread? You take the values, all the values, and take the difference from the mean of the data, and then square it. You want to square it because you don't want that if you have equally distributed, some data distributed here, some data distributed here, you don't want that you take this number, subtract from the mean, you get some positive x, but this will give you a negative x, and they will add up to 0 if you will compute the average of this quantity. So you don't want that to happen. So to cancel these negative numbers, you take a square. So you are, in a sense, computing the average of the spread. And that's the formula. When you take all data points, but by the same logic as we used before, you can take all values instead of data points. Then instead of dividing by the total number over here, you can multiply by the probability distribution or frequency. This is probability or relative frequency, which is frequency divided by the total number of elements present there. If you look at it, this is the same formula as of an average of the mean, which we defined above, but mean of this quantity. So that's the variance. So what would be the variance of sample mean? If I use the same thing, sample means are hopping, but they have a expectation value, which comes over here, which would actually be equal to the population mean. And then you take a difference with each sample mean value, multiply it with the probabilities. Well, I have to square it, and then the sum. Now you have this result. If I do this, take this formula, I can again prove. I'll probably leave the proof till the end, or maybe put it only in notes, not do it in the lecture, because probably it will bore people out. But you can prove it very easily, not too difficult, that if I compute the variance of the sample mean, so this spread, some idea about this spread, what is the average spread around the central value, according to this formula, then it will come out to be whatever the variance of the original population probability density is divided by n. So variance of sample means is variance of probability distribution divided by n, where n is the number of samples. No, sorry, not the number of sample, size of the sample. Please don't call me. So now this standard deviation of the from this thing that you have the variance of the sample mean, you can also define something, some quantity which is very closely related. This is called the standard deviation of the sample mean. I can write it like this. This is the variable whose standard deviation I am computing, and it's denoted by sigma, which is just the under root of the variance of the sample mean. So what I have found that this would be equal to the variance of the population, divided by n, but the square root of variance of population, I can call it the standard deviation. This is the standard deviation of the population. So remember, population is spread as well. So if I draw these values of this variable x in the population is spread as well. There's some central value, which is the mu, but there's a spread in the population, which is quantified by this thing sigma. If I apply the same formula to the population distribution, I'll get a sigma. And when I'll apply the same formula to the samples, I'll get sigma, which would be standard deviation of the sample means. And the formula is saying that when you pick the samples, then the standard deviation of the samples is reduced according to how big of a sample you pick up over here. And this thing, the standard deviation of the sample mean, it's also given another name. It's also called standard error. So what's the logic of this name? This name is actually quite revealing. It says that you pick up a sample and you want to estimate something about the population. And in this case, you are trying to estimate the mean of the population. So what it says is that you will not get the mean when you pick a random sample. You can hit the mean, but not necessarily. You will be somewhere around the mean. And you expect a certain amount of error that where you will land. And that is quantified, that how big of an error you expect by this standard deviation. So that's why you call it the standard error as well. Now, again, there are many questions.
Sir?
जी.
Sir, standard error को हम minimize कैसे कर सकते हैं?
Well, one thing is over here. It shows you that if you increase n, this small n, you have no control over how the population is behaving. Population has a certain probability density, but the standard error can be reduced just by increasing n. So increase the size of the sample to reduce the standard error.
So is that why we use the n-1 in the formulas?
No, that's not the case. That I'll come to that later, not today. So in these formulas, you don't use n-1, you use n. So, so that means if you want to get a good estimate about the mean value of the population, you should be picking bigger. You don't want to encounter a big error, then pick bigger samples. The bigger the sample you have, the better is your estimate. Still you can be off because it's all probabilistic. By chance, by very bad luck, you can still be way off, but you have a much less chance of being very much away from the center, from the population mean, if you pick a bigger sample. That's why when people uh, do these studies, like you must have, like for example, heard about these election uh, uh, surveys. So when people ask about it, the bigger the sample that survey has, the less error you expect coming from just from the statistical variation. So even if you don't put in any bias from your side, if you pick the samples completely randomly, you're completely sure that your sampling methods are random, you're not putting in any bias, you still expect errors because you're not sampling the whole population, and that's is called a standard error or statistical error, which is just there because you pick a finite sample. So any question about this one?
Sir, so far so good.
Okay, now this formula, so this is a important formula. This is true, strictly true, only for very large population. Large compared to the sample. Like if you're picking a sample of 100 and your population is 10,000, then this is good enough. But if you have a finite population, then this formula is not strictly correct. Instead, what you have is the following: that the variance of the sample mean, according to this formula, you expect it to be this one, right? Because standard deviation square is just the variance in the population. But that's not the exact formula when you have a finite population. The correct formula is this one, where n is the size of population and small n is the size of,
Sir?
size of sample. So you can see when big N is much bigger than small n, then this formula becomes this formula. Because I can write it, I can divide by capital N above and below, what will I get? 1 minus n over n, 1 minus 1 over n. So when n is very large, this becomes 0, and this also becomes 0. So this goes to, so from this you can estimate that how big of a difference does it make. Not a lot. Like if you are picking 10 elements from 100, then this is just 0.1, but it's being divided by almost by something which is also has some factor. So you are making a difference of 0.1. But if they're very close, like in our example, we had 6 members and we were picking samples of 3, then if you want to get a good idea of variance, then you should actually be using this exact formula if they are close to each other. Yes, there was a question.
Sir, I wanted to ask, how can you determine कि मतलब इसमें अभी finite population correction लगेगी कि नहीं लगेगी?
Well, there's no, like, it depends on your kitni accuracy pe aap jana cha rahe hain. So you, first of all, you can always use this. This is because this is an exact formula. मगर you can quickly have an estimate by doing this कि कितना फर्क पड़ रहा है. So like
Okay, sir.
if from this factor, if this factor is like 0.01, then it's not worth it. So it depends on how much accuracy you want in your estimate of the variance of the finite population, of the population.
Okay, sir. Thank you.
So let's do this example of applying this formula. Now, let's go back to the example which we did last time as well. You are doing coin toss. So you can imagine that you have an infinite number of coins available because you can toss them an infinite number of times. And from that, there's a distribution over there, probability distribution. What is the distribution? Probability of tail is half and probability of head is also half. So you can draw tail, head, and they both have same histogram. There's a probabilities over here, and both of them have a probability of half. And I'm giving them values 0 and 1. So 0 turning up has a value half, 1 turning up has a value half as well. So the population mean, which is mu, according to our formula, is just half, which makes sense. This is 0, this is 1, and they're equally distributed. So as you expect, the mean is in the middle at the value half. And you want to see what is the population standard deviation, sigma. So what do? You have the first value minus the mean multiplied by the probability of this happening, and this squared, plus the second value minus the mean and probability of this happening, and this squared. So this is 1 by half squared, half, plus 1 by half squared, half. This is variance, sorry. I will then have to take a square root to get the standard deviation. So I get 1 by 4 times half plus 1 by 4 times half. So I get a 1 by 4 square root. So I get a standard deviation of half, which gives me a very good actually estimate, because it says that the central value is here and I have standard deviation. I expect to deviate by half on each side. And that's a very good estimate. Like most of the time I do end up, well, all the time, in this case, all the time you end up at the standard deviated value. So, but this shows you that this number is a good estimate of how much this distribution is spread. Now, from this distribution, I pick samples of size 2. So what are the possibilities? I pick the first coin, I got a head. The second coin, I again got a head. So I got 1 and 1. The mean is sample mean. This, I should call it the sample mean, is 1. Then I could have a sample like this. A sample mean is half. I can have a sample like this. A sample mean is half. And this has a sample mean 0. And they're all equally likely, all these samples. So I can compute the variance of sample mean would be, I can just do it by the first formula, which was that you add all of them. The first half is coming from the mean, because I know that this that the expectation value of the sample mean is going to be equal to the population mean, which in this case is half. So I already know, I don't need to compute, that the mean of the sample means is equal to population mean, which is half, which is the number coming up here. Wait, don't ask any question right now. And you divide by all the values which you have. So you have 1 by 4 plus 0 plus 0 plus 1 by 4 divided by 4. So half times 1 by 4, you get 1 by 8. And standard deviation is square root, which is this, which turns out to be about 0.35. So what you have got is, by picking samples of size 2, instead of having a standard deviation of 0.5, you have reduced it to 0.35 because you divided by 1 over under root 2 according to this formula. Well, there's an under root n here because you took a square root over here. So you got this over here. So any question? Question? Let me do it again with a different sample size. Now you are taking samples of size 4. Again, you have this distribution, which is fixed. It's the same distribution, but now I'm picking samples of 4 coins. What are the possibilities? I've listed all of them here. You get all heads. You get the first 2 head, third head, and fourth is the tail. All these things are possible because at each point, each one of them is equally likely. So they are all equally likely. And I have just computed the means. So what is the mean over here? A head is 1. So 1 plus 1 plus 1 plus 1 divided by the total sample size, which is 4. So I get 1. Here I have 3 heads. I add them up. Tail is a 0. It doesn't contribute. And divided by the total sample size, I get a 3 by 4. Here I have 2 heads. I get a 2 by 4. So depending on how many heads, I get these numbers. So I have listed that what are the possibilities of mean. There are only these possibilities. I can get a 1, I get a 3 by 4, 2 by 4, 1 by 4, and a 0. And what are their probabilities? I just count how many times they appear. So in this case, I am drawing their probability distribution. I'm inferring what is their probability distribution. I can actually draw it here. So I have a 0, 1 by 4, 1 by 2, 3 by 4, and 1. So 0 has a certain probability, which is 1 by 16. 1 by 4 is 4 times as likely because it's 4 by 16. This is its probability distribution, probability. And 3 by 4 also has the same. 1 has, again, 1 by 16. While half has 6 by 16. So I have drawn the probability distribution of the sample means for samples of sizes 4. Now, using this data, I can compute the standard deviation of the sample mean. Well, let's go one step by step. Let's first compute the variance of standard mean. Let me just take a break for 2 minutes.